All right, so let's talk about boundary conditions a little bit, and I'll kind of go over this systematically in the context of the problem that you're going to solve in homework 5. Okay, so this is sort of supposed to be a guide for you for your code development. Okay, so this is the problem that you're going to solve. Many of you have seen this problem. This is a very classic benchmark problem in CFD. Many people have solved this problem. There are many published solutions out there. People have even done experiments on this. Of course, experiments you can't do in 2D, you have to do in 3D. But we are going to talk about the 2D version of the so-called driven cavity or driven lid problem. Okay, that's what it's known as. So the idea is very simple, that you have a tank full of a fluid. That fluid could be water or gas, it doesn't really matter. And you have a lid on top, okay, which is moving tangentially to that plane. Okay, so when it moves, obviously it's because of viscosity, it's going to drag this fluid right next to it, and that in turn is going to create this recirculation pattern. Okay, so the fluid, this fluid will get dragged, it'll hit this wall, and obviously it has to take a turn, and then because of viscosity there will be some smearing effect. Okay, now depends on the Reynolds number, this problem can produce many interesting solutions. For example, if the Reynolds number is fairly high, what will happen is this guy will hit this wall and then bounce back almost like this. Okay, so it won't sort of follow the right wall, it will get away from the right wall and then create a recirculation pattern, and you may get a secondary recirculation here and a smaller one here. Okay, so again, depending on the Reynolds number, you will see different flow features show up. It's an interesting problem. Once you solve it, you will also see that I'll ask you to actually solve this at 2 different Reynolds numbers. You will see differences in the solution in the 2 cases. Okay. Just as a brief heads up, okay, so I already mentioned that the fluid is getting dragged by this plate. Okay, so you expect that here, right here, is going to be high pressure in that corner because the fluid is going and hitting that corner. Okay, so there's going to be high pressure here. On the other hand, this corner here is like a suction zone because the fluid is moving out there. So this is going to have low pressure. Okay, high pressure. So this corner is going to have the highest pressure of everything. And then as the fluid starts recirculating, as you know, this is the eye of the tornado or the eye of the hurricane. That's where you'll have small pressure. Okay, so you will have a blue region here for pressure if blue is low pressure and red is high pressure. And then around that you will start developing these pressure contours. Okay, so these are just some symptoms of the solution that I'm telling you, so you can kind of check to see, okay, am I getting something in the right ballpark? Okay, any questions? So this is the problem we are going to solve. So now the question is, what are my boundary conditions? Okay, so I'm going to start with now one other thing I want to mention here in terms of boundary conditions, because this is something that's a bit confusing. So sometimes we may have, so in this case, the lid is moving tangentially, right? So which means that the total volume is fixed, it's not changing. What if the lid was moving vertically? Okay, that you have to, it's a special class of CFD problem where the volume itself changes. In other words, you have a moving mesh problem in that case. Okay, so all your governing equations will have extra terms due to the moving mesh. So your continuity equation won't be ddt of rho u plus divergence of rho u equal to 0, or ddt of rho plus divergence of rho u equal to 0. There will be another extra term which accounts for the change in volume. Okay, so keep that in mind, that this is a moving boundary problem. The other one I mentioned, where the lid moves normal to the surface, is also a moving boundary problem, but that's a special class of moving boundary problem, where the mesh itself has to move. Okay, so Another problem that we often encounter, and you all know this, and students often ask me, okay, what's the difference? So you mentioned that if this moves normal, then it's a moving mesh problem. What if this is an inlet? Okay, so there again, the fluid is moving normal to the surface, right? But again, this is not a moving mesh problem because this volume that you had right next to the inlet stays the volume. The volume is not shrunk. The volume gets shrunk only if it's a solid wall and it's moving. Okay, so an inlet, conceptually, you can think of it as a moving boundary because you can say, okay, U in is the same as U lid because both are moving. But fundamentally, if you look at the governing equations, they will not be the same in the two cases because in one case, the volume shrinks, in the other case, the volume stays constant. So an inlet is not the same as a moving mesh problem. Okay, so keep that in mind also when you're working with these kinds of situations. Now, none of this you'll be doing in your homework, but I'm mentioning all this because you may encounter such situations for your research or some code that you're developing. Okay, so do not classify inlet and wall moving normal to the fluid as the same. They will not act the same way. Okay. All right. So let's talk about this particular case now, where I have one wall moving tangentially. Everything else are fixed walls. Okay. So viscous drag forces the fluid to move and sets up a recirculation pattern. I already talked about this. Secondary vortices may be formed in the bottom left and right corners, depending on the Reynolds number. So let's talk about the X momentum equation first. Okay, left and right walls, and here I'm showing you an example of a left wall. And now I've also drawn my staggered mesh because I have to worry about everything in the context of a staggered mesh. Okay. So now I already mentioned that for the X momentum equation, you actually have a node or a cell center at the boundary. Okay, this is kind of weird because normally in finite volume we wouldn't have that. But because we have staggered the mesh, we have that now. Okay, so this guy is already known. This velocity is 0. Okay, so the first unknown is 2 comma j, not 1 comma j. All right. So I want to set up the boundary condition for this particular control volume. Okay. Now, it so happens that this control volume, as you can see, is really an interior control volume. It shares no face with the boundary at all. Okay. In fact, it does have a western node, just like any other interior control volume, except that the western node velocity itself is known. Okay. But in terms of, if you think about developing the finite volume equation, it is no different than an interior control volume because it is actually interior. All right, even though we are thinking of it as a boundary control volume. So therefore, we can start directly with our discrete form of the X momentum equation rather than having to go back and think about, okay, how will certain flux terms change? Because it is an interior control volume. The only thing we have to now worry about is we say, okay, my western phase velocity or western cell velocity is already known, and that's 0. Okay, so that's this guy here. So I'm just going to set that to 0. That applies my boundary conditions, and the rest stays the same. Okay? That's all. Everybody with me? So this is all you do for the left end, and the same thing will happen at the right end. I'm not deriving it for the right end, but the same idea. You will look at, so on the right end, you will have a node or a cell at n plus 1, un plus 1. Okay, and you're developing the equation for un in that case. All right, and the eastern velocity will then be set to 0. Any questions? Okay, let's move on and now talk about the bottom wall for X momentum. So now we have a different scenario completely. Again, this is all due to the staggering of the mesh. Things become quite non-intuitive. As you can see here, this is also a wall, but there are no cell centers on the wall, unlike the left and right walls. Okay, at the bottom wall, we actually have a control volume adjacent to the wall. And the cell center is just like you have in a collocated mesh. Okay, delta y over 2 displaced from the wall. So we're trying to develop the finite volume equation for this control volume now, okay? So this is not an interior cell, this is clearly a boundary cell, and therefore we are going to get back to our basic flux balance, okay? And I've said this many times, do not ever apply boundary conditions on the discrete equation unless you have a situation like this where you know this is an interior cell. I've already derived the equations. Nothing is going to change, okay? I'm simply going to set one of the velocities to 0. But if you have a volume which is right next to the boundary, adjacent to the boundary, you must go back to the flux equation, okay, rather than try to apply boundary conditions on the discrete equation, okay? So go back to your flux equation. This is what your flux equation looks like. So we have east minus west, north minus south, equal to whatever you have for your pressure gradient. I've highlighted one term here in red, and that is because that is for the southern face, which is a boundary face. Okay? So we need to figure out what this flux expression is for the southern face, which is this face right here. This is my small s. All right? So all terms stay the same except the s term. Clearly, the first advective term, this is equal to 0. Why? Because we have no slip boundary conditions at the wall. So both Vs and Us are 0. All right? So that's pretty straightforward. Then we get to this term, the diffusion term. To derive du dy at the southern face, you have to take two Taylor series expansions like you just did for the homework problem that you turned in, homework 2. This is the same as standard finite volume formulation. Once you apply the two Taylor series expansions, you get this well-known expression with a 9, 1, and 8, 3 in the denominator. This is second order accurate. Okay, so this is your du dy at the southern face. Okay, so you plug that in. And of course, the u south, this is where you're applying the boundary condition. In that expression itself, the southern face velocity itself is 0. So you set that equal to 0, you're left with just two terms. Okay? And then you plug that in and rearrange your equation, and this is what you get. You get an extra contribution to the north. Why? Because this one had a u north. Okay? And then another contribution to the diagonal, all right? So that's what you have here, a contribution to the diagonal, a contribution to the northern coefficient. Now, if the velocity at the bottom wall wasn't 0, then you would get a contribution to the source also, which I will show you for the top wall, okay? And then everything else stays the same. So what we're doing here, you know, if you ask me, okay, how did you come up with these coefficients? All I did was I looked at what contributions I have from the southern term, okay? Then when I wrote down these coefficients, I simply deleted whatever contributions I had for the southern term and then replaced it with what I got from my new derived expression, okay? And those terms are very easy to identify in the expression because every term has a east-west, north-south subscript associated with it. So you just look at the southern terms and you say, okay, I'm just going to throw them away first, or if you're working with a pencil and eraser, you just erase them out, okay? And then you look at your new expression and say, okay, what is that now giving me in these equations? And you find that there is a contribution to the north, one contribution to the diagonal, and that's it, okay? In terms of coding, you can do the same thing, but again, I urge you to be very careful if you copy and paste. You can copy and paste your interior cell equations to here, okay? Get rid of the southern terms or delete them, and then put in the new contributions. Same idea, okay? All right, let's look at the top wall, because the top wall is very special. Here we have a northern u velocity, which is u lid. Okay, it's not 0. So if I now look at, so I'm not going through the derivation, if I go through the derivation like I did here, okay, do two Taylor series expansions, I'm going to get a U naught, U south, and then instead of U small south here, I'll get a U small north, okay, in that expression, because du dy at the northern face is what I'm deriving now, okay. And that velocity is not zero, so that will also give me an extra term in my source, okay, which looks like this. This term was not there in here when I did the southern face because my U south was zero. In other words, instead of U lid, I had a zero, and so nothing showed up there. Okay? Now, I just want to kind of point out here that suppose you want to solve this problem here, this driven cavity problem, and you start with P equal to 0 everywhere as your initial guess, U equal to 0, V equal to 0 as your initial guesses. Like I said, best, that's a reasonable guess. Now, P, of course, remember, this is gauge pressure. You're guessing that gauge pressure is 0, which means pressure is uniform everywhere at whatever the reference value is. All right? And then you're setting U equal to 0, V equal to 0. Now, if you think about it, if I use those as my initial guesses, couple of things are going to happen, and this is where you need to really have a good understanding of how your code works and how you debug it. So first iteration, if you set U and V equal to 0, what will happen is all your advective links will go to 0. All those switching functions and everything will be 0. The only non-zero terms will be your diffusion terms. So if I look at my link coefficients, for example, I had it here. You see all these guys will go to 0. Nothing will exist if I set velocities to 0. Only terms will be left over are these diffusion viscous terms, right? Source will also be 0 because I've set pressure equal to 0 everywhere, right? So when I solve my momentum equation, it's almost like I'm solving a Poisson equation for velocity, a diffusion equation. Right? Now, if I have everything as if my entire source vector is 0, like we are saying here, then of course the solution is going to come out 0. Because there has to be some source. I mean, if I just solve all equations equal to 0, the final solution will be 0. Okay? So there has to be some source. Where does that source come from? This is the source that's going to finally drive everything. So there will be one element or a bunch of elements for the northern row of cells which will have non-zero source because of this term. Okay? And that's what's going to finally give you a non-trivial or non-zero solution for the U velocity after the first iteration, the very first time you solve your momentum equation. Okay? So the very first time you solve your momentum equation, let me draw a picture here. So here's my cavity. Okay, here's my U lid. And if I asked you to plot U velocity contours on this, right after you've solved the X momentum equation with initial guess of U equal to 0, V equal to 0, P equal to 0, what do you think you'll get? Okay, so obviously let's say velocity is 1 here. Okay, so what will the contours look like? Yep, so you'll get these. Like that. Okay, maybe 0.9 here, 0.8 here, 0.1 here, and pretty much 0 everywhere else. Why do you think you'll get that? So first of all, will these contours be symmetric between left and right boundaries? Yes, no. How many say yes? So majority say no. So why will there be asymmetry? Pressure is 0, first iteration. Uniform everywhere, no pressure source. So the equation really that I'm solving in the first iteration, first outer iteration, is really this. Because everything else has dropped out. There are no advective terms. There are no sources, right? So your Navier-Stokes equation has really reduced to this. So do you think the solution of that will be symmetric or asymmetric? Symmetric. This is exactly like a heat transfer problem where you have a specified temperature of 1 here and 0 everywhere else. And you're solving the conduction equation, del squared T equal to 0. This is what you're going to get. Okay? Now, this velocity field, and V will be 0 because V, the entire V, Y momentum equation has no source. This source that I showed you here down below, this one, this doesn't apply to V because V lid is 0 still. Okay? So when I do the same discretization for V velocity, there are no sources. So V, the solution for V will be identically 0 everywhere. The very first time you solve it. Again, I want to emphasize, this is all with initial guess of U equal to 0, V equal to 0. If you do not use initial guess of U equal to 0, V equal to 0, then these profiles will no longer be symmetric because what will happen is now flow will push that profile this way. Okay, it will get skewed. If, for example, you used a positive U velocity. All right? Everybody get that? So, why am I talking about all this? Because these are the things you need to look for in your code when you develop the code. You should solve your X momentum equation, and I'm going to tell you this again and again. Go back and solve your X momentum equation very first time to machine accuracy and come back and show me the solution. If it doesn't look like this, then don't tell me that my Navier-Stokes equation is diverging and this and that, because you haven't even crossed the first barrier. Your first job is to get your X momentum equation working correctly. And this is what we called in the first lecture a sanity check. Getting this profile for U and 0 everywhere for V. Okay? Now, sometimes students will come and tell me, well, I did that check, here's the convergence, here's the solution, everything looks fine, but then second iteration something weird happens and things just blow up. Okay? So what do you think is going on then? Any idea? So if it's working first iteration, let's say you've checked your U momentum, you've checked your V momentum, both are working, okay? And let's say somehow you've also figured out your pressure correction equation is working correctly. But then you find second iteration, first iteration everything works, second iteration, boom, residual goes to 10 to the power 34. What may have gone wrong? How are you going to debug it? Pardon me? Very good, very good. So here's the thing, okay? Again, first iteration, when you set U and V velocities to 0, all these link coefficients dropped out. All these guys. You were left with only the diffusion links, okay? These guys. So what does that mean? Second iteration, your velocity has now become non-zero because you've already solved the momentum equation once and I already drew the contour profiles, right? So your momentum coefficient, your velocities are no longer 0, which means second iteration, these advective links will get activated. And if you have a bug in one of those, your code will blow up. So the first iteration gives you a sanity check of just the diffusion terms. Second iteration, once it works, then you can be almost sure that your momentum solver is working. All right? Now, one thing you could also check is you could say, well, I know what the solution is going to be in the pure diffusion case. How would I know if with advection it's working correctly or not? Well, what you can do is you can set your U lid to be a very, very small value so that the solution is still diffusion dominated and it would still look like the first iteration solution. Okay? So, I mean, those are all different things one could do to make sure that you're on the right path in developing your Navier-Stokes solver. Okay, so everybody clear on where the non-zero solution starts from? That's from this term right here. Okay? At least for this problem. Now, Y momentum, same idea. For top and bottom walls, follow exact same procedure as left and right walls for X momentum, okay? Because you're now going to have nodes, V nodes for the top and bottom walls, okay? So I'm not doing anything here. For left and right walls, follow exact same procedure as top and bottom walls for X momentum, except that, of course, you don't have V naught as equal to some value. Both velocities will be zero, both on left wall and right wall, okay? But that's the idea. Okay, let's talk about pressure correction. So pressure correction equation, as we know, is derived from the continuity equation. That's the physical basis. Ultimately, we get this artificial equation for pressure correction from the mathematics. But really, that equation has very little physical significance. In other words, if I told you, you know, how do I set boundary conditions for this equation, I would have no clue, because that's not the real physics. That equation is not the real mathematical model for the physics. The real mathematical model is the continuity equation. So that's what we need to start with, okay? So starting point of derivation of any boundary condition for the pressure correction equation should be the finite volume form of the continuity equation, all right? So let's talk about left wall. So now we have a control volume, which is our green control volume, right next to the wall. Okay, so here is our continuity equation. Again, I've highlighted the western term because that's a boundary face. Okay, so right here is your western face, which is your boundary face. Okay, so what do I do? Well, set it equal to 0 directly, because we know that the velocity at the western face is equal to 0. Set it equal to 0, that term completely drops out. For the rest of the terms, you simply use expressions for these three, like I've done here, straight out of your notes for interior faces, because this, and that, they're all interior faces. Okay? And then you derive your corresponding link coefficients, your mass imbalance, and there you go. Essentially, all that has happened is I've just taken my expressions for the interior control volume and just erased the western terms, because the western velocity goes to 0. Okay? And I get this. Any questions? So right and bottom walls follow the same procedure. If you are in a corner cell, then 2 of these terms will drop out. So for example, if you are in a left bottom corner, then the western and southern terms will drop out. Okay? And you'll just have 2 link coefficients. You'll have a north, and an east. That's it. Everything else will drop out. So it's a combination of two procedures. Any questions on that? It's pretty easy to follow. Okay, for the top wall, even though the U is equal to U lid, V naught is still 0. So recall, okay, your continuity is this. So the fact that on the northern wall I have a non-zero velocity doesn't really matter, because the northern wall never sees U in that direction. What it sees is the normal component for mass conservation. Okay, the fact that this lid is moving has no bearing whatsoever on mass conservation.